here. Before we begin today's lecture, I want to clarify something in the homework 2. It talks about solving graphically. So for one segment functions, remember what the segment is here's our cost curve, and a single segment means a straight line that does that. 2 segments means that you're going to take the same curve and you're going to go about, whatever halfway is, and you're going to have 2 segments, etc. And then the program that you have just keeps dividing. But I said, let's solve this graphically. Well, okay, so here's the cost function is this. It's the line. It's it's not the curve, it's the line. So if this is f of p, then df of p dp is a straight line. So it literally looks like that. Over here, df dp is going to look like this. I got it about halfway out, and then it's going to come up. Those should line up, but it's got 2. Here's f of p with a 1 subscript, and here's f2 of p, the second segment, and so here's df1, dp1, and here's df2, dp2. Now, how would you solve such a thing graphically? It is certainly possible, and when I show you, you're going to say, "Oh, well, this is kind of trivial." It's not trivial. Let's say I had 3. I have 3 generators. So here's my 3 generators, and I'm going to assume that the first one looks like this. The second one is going to look like this, and the third one we're going to make it really, really steep, and it's going to look like this. Okay. Now, what do the DFDP look like? Well, they look like this. They just look like, okay, it's a number. It's right across the middle. This one is got a lower slope, so he comes up like this. This one has a higher slope, so he comes up like that. Okay. And once again, the points are points off of the actual cost function, and so for the one segment, it's the low and the high p sub I. It doesn't have the f and the f value of that point is really this is f of I of pi at pi equals min, and this is f of I of pi at max. And the slope, you can argue, okay, what is the slope? Well, the slope of that thing is just it's a triangle, so it's the difference between those 2 values divided by the max minus min, and you can get the value of the slope, which is going to go up and down. Well, now if I have 3 things like this, if I put my ruler and I say, well, lambda is this real low number, well, then all 3 units are on their min, and we would start. I would say, well, that doesn't give me the load, so raise the value of lambda. Well, now, once you get lambda up to the lowest one here, then this one starts to come across. You can keep these at their min, and let this one come across until it gets to its max. So the next one is this one. It's as if it goes up, and then it goes over, and then it goes up. Okay. The only way to picture that is to say, well, it's not a perfectly flat function. It's just got a tiny little bit of rise. So as I raise the lambda, it edges its way across here. Now, this min, this max, this min, if I'm still needing more generation, I keep raising lambda until I get to this point, and now this guy will go across. Well, eventually, I'm going to get P1 plus P2 plus P3 equal to the load that I'm trying to, which is 450. And that's the solution that you would get from this straight line function. See if that is what matches the LP. Then you go back, and do it with, let's swap out the pad here. So now let's say I've got, two functions like this. And over here I've got two functions, two segments, pardon me. And I have two. So here's 3 units. Do the same thing again, only now I get a two-step incremental. This is df dp for 1, and this is for 2 and for 3. And so I don't know, maybe it comes up like this, and maybe this one comes up very steep, and he comes up and then up. These do not line up. I'm not trying to draw it very carefully. Now you just do the same thing. Just start with a lambda down at the bottom. Everybody's at minimum. And start raising it until one of them creeps across here to this point. And you keep going like that. And until you get a solution. And in the first problem, at least one of them will be between min and max. It'll be coming up. Okay, the second problem will probably be a couple of those. And then check that against what the program got with linear programming, just so you can see how you can do that. Now, it turns out that linear segmented f of p, part of what I wanted you to realize is that there's a lot of problems that I can solve with linear programming by dividing nonlinear functions up into segments and considering them to be straight lines in the segment, and then I can solve. Okay, that's what that is, and I'm not going to ask you to do it for 5 or 6 or anything, because you'll go crazy. Moving rulers around on graph paper and so forth, but for the 1 segment and the 2 segment, you can almost do it with just very quickly by eye, just looking at it with your eyes. Otherwise, draw them on a piece of paper. Take a piece of a straight edge, a plastic ruler or whatever, and start doing that. Okay, that's what that was about. Somebody had written an email. And I can see that needed some explanation. Okay, now the next topic. Let's switch colors here so that unit commitment. By Lagrange relaxation. I want to make a comment here, where if I can find the note on. It's a page in the book where there's a footnote. In the footnote in the book, it's in the copy I'm using, which is one of the pre-published copies of the book. It's the page with figure 4.6, but it may be earlier or later than that figure. There's a footnote. It's footnote number 1. Bertzikas, Lauer, Sandel, Posberg, T.A. Posberg. This was one of the pioneering papers in this field. You'll notice that I just noticed this now, that it says optimal short-term scheduling of large-scale power systems, IEEE transactions on automatic control. what happened to IEEE transactions on power systems? I have a feeling that these authors at that time were used to sending papers to the automatic control journal, so that's where they sent it. And it was a pioneering paper. Bertsikis was a professor at MIT. But one of the things I want to point out to you, I don't know if this is if you haven't done your undergraduate at our department at Minnesota, then this may not come. Tom Posberg, T.A. Posberg, is a teaching staff in our department. He works in our department. He is a good friend of mine, and he was one of the people. I remember one of my students coming in with this paper and saying, "This is the paper that shows everything." And I looked at it and I said, "Posberg, that's Tom Posberg." And I went over and I said, "Were you the Tom Posberg?" And he said, "Yes." So, one of our own staff people is one of the original authors on the original papers for Lagrange relaxation applied to generation scheduling. Now, I indicated that the market today has shifted once again. So we've gone from dynamic programming to Lagrange relaxation, and now people are using this IBM product Simplex, Cplex, pardon me, and it's a massive program, but it solves it by 1-0 programming, and people feel that it gets closer to the optimum. We're going to see that the Lagrange relaxation cannot guarantee that it is at the optimum. And so the 1-0 programming routines, they feel get a better solution. Okay, now let's come back to our basic problem now, and we're actually going to do the formulation as if we're doing it with 1-0 programming. It's the same as we see in this Lagrange relaxation. So we're gonna have a variable u, and it's gonna have a subscript t. Or am I reading this wrong? I'm wrong. I'm sorry. U, superscript t, subscript I. T equals an indicator for a time step or an hour. I is equal to a particular unit. Unit I, okay? Now, and this is equal to it's either equal to 1 or it's equal to 0. Thus, the definition 1-0 programming. One of the harder means of solving one of the harder programmings to solve when you have 1 and 0 variables that can only be 1 and 0. So, what we're concerned with now is saying, well, okay, now I'm gonna redefine the unit commitment problem, and then we're gonna look at some examples, and I'm going to have you in the homework. I'm going to assign you to solve a problem in the that's in the book, okay? Using both dynamic programming and Lagrange relaxation. All right, so we have, remember, for every problem, even economic dispatch, we have a load constraint, but we have one for each hour t. That's the and that constraint, which we will call 1 right now, is P load of T. There's a load at each hour minus the sum Pi T Ui of T. And now this is summed over the units. I equals 1 to n equals 0. Now, if all the units are off, and that's the 0, meaning they're offline, they're not connected, they're not synchronized, they're not supplying power. If they're all off, well then this constraint is not going to equal 0. It's going to have a positive number on the left-hand side. And we want the sum of the output of all the units at a particular hour, which those units which are on, so I only need to look at the ones that have a 1 here, and the sum of those units has to equal the load. Well, that's our economic dispatch, but it's resolved every hour, every time step t. So you go t equals 1, and we use a capital T. If you ever see earlier editions of the book, you'll find that we used to use capital. We used to use letter. The main numbers up here were capitals with subscripts, and it just got to be too messy. So we said, okay, T is the number of time steps, N is the number of units right there. Now that's basic. Every hour we're going to meet the load, and if you will, it says that means that here's hour 1, 2, 3. That there's a value of load for each hour. Okay, and let's say here's the load and it's going up. Okay, so here's this is P load 1, P load 2, P load 3, and it can go up and down and up and down. Okay. So we have broken the load down into stepwise approximations, a fixed number of megawatts per hour. Okay, that's the first constraint, and we've got those 1, 0 variables in there. And now I'm going to do constraint number 2, which are just unit limits, which are very simply Ui of T, Pi min is less than or equal to Pi of T is less than or equal to Ui of T Pi max. You don't need to multiply the middle part of the inequality, two-sided inequality by Ui, because it's there, and these are the same variables. So this just says that if the unit is off, well, if the unit is off, then 0 must be less than or equal to the output of the unit must be less than or equal to 0. It must be 0. That's the only way to get that. If the U is 1, you have your normal upper and lower bound. So that one is fairly simple. So now we have the loading constraints, and we have the generator up-down limits, which depend on the UI for that unit at T. So I want to emphasize. I'm going to put this in red here up at the top. Ta-da! Let's see. I've got to put my page number, but let's I'll put it right here. Variables. Let's see. I have UI of T. So there's 1 per time step and per generating unit. Okay, so there are n for the number of generating units times t variables, Ui of T. So there's a lot of those variables. Okay, Pi of T is again the same thing. There are n times t of those variables. there's one per time step and per generating unit. So there's NT variables. Lambdas later on, we're going to get lambdas. They only have a T. So there's only T lambdas. Lots and lots and lots of variables in this program, in this method. All right. We describe the fact that there are min up, min down constraints, and air quality constraints. There are all kinds of other spinning reserve constraints, and so on and so on. We're not going to get into that at this point, although we may deal with some of these later on. But they're minimum. They're each generating unit. Again, min up says that the unit goes up, and maybe it's got a min up of 3. Then it has to stay on for 3 hours, and then it can come down. So if it goes 1, then it's 3 ones in a row. Then it can go to 0 again. Okay. Now, the next constraint is to get into our objective function. This one we're not going to come back to. The objective. Okay. In other words, what we're going to minimize. We're going to minimize the sum of the Fi of Pi of t plus its startup which is a startup cost and it really just has to do with a particular generator. Now, times ui of t, and this goes I equals 1 to n. Now that is the economic dispatch program. What am I minimizing? Well, not economic dispatch. I'm not looking at startup, but this is the cost to operate in a particular hour if I started the unit up. And this is the economic dispatch if the unit is going to be on that hour. Ui of t equals 1. If ui of t equals 0, well, there's no cost contribution. And then I have to minimize that over t equals 1 to t. Okay, so here is the double sum, and the double sum is what makes the problem so complicated. It's the sum of the total operating cost over hour 1, the sum of the total operating cost over hour 2, and so forth. And the total operating cost is the sum over all the units. So for hour 1, you sum over all the units that are on. For hour 2, you sum, and you have to know, what is this ui of t? The effort then is to find the ui of t for all the time steps and all the generators. Now this is equal to, we call it f of pi of t ui of t. Okay. All right. Then we're gonna form our Lagrangian, and we'll start out here. We say L equals. I'm sorry. Let's put the variables. L of P, U, and lambda equals. Well, it's my my f of p. It's this function, f of p I of t u I of t plus the sum lambda of t times p load t minus the sum I equals 1 to n p I t u I t. Now, one of the things that I start talking about right away is that if it weren't for the loading constraint, which sums over, time steps, t t equals 1 to t. If it weren't for the loading constraint, well then it would just be a series of completely disconnected economic dispatch problems. The series of dispatch, but we're trying to minimize the cost that's added up over many hours, and so if I dispatch during the first hour, that might affect how I dispatch the second hour, and so on and so on and so on. You can't simply come along and say, well, for each hour I'm going to do an economic dispatch. I could say, well, for economic, I ignore the time variable. I ignore that time variable. Are there trade-offs? Yes, there are. There are definitely trade-offs, especially we get into this problem. So, and I'm kind of going through this. This is as if you've seen the lecture on the CUSP website, and this gets to be, and I'm trying to emphasize now the where we're going to go with this particular problem. But remember, this is L. Okay, this is L, and we're going to define a function Q of lambda, which is to say that function is the minimum value of the Lagrange function of P U lambda over P and U with lambda fixed. That's Q. That's the initial Q. And we're going to say, we say Q is the minimum of the Lagrangian when the Lagrange multipliers are fixed. I will come back to this in a little while. And then, given the solution, get P and U. We'll just put an asterisk. That's the solution. We're gonna go up now, and we're gonna say, well, now the next step is to maximize Q of lambda over lambda, with P equal to P star and U equal to U star. So this is the decoupling. I'm going to solve the problem with lambda held constant. Remember that the definition of a relaxation procedure is that you've got some variable it's a variable. It's going to move up and down, but for a part of the solution, I'm going to consider that variable to be fixed. There's a good example of this in the Appendix 4A. We did an example, and it actually, I think, pretty much comes from the constraint optimization example from Chapter 3. And the idea of that example is that you can see that there are two variables, x1 and x2. There's a u1 and u2. So we are saying in that sample problem that there's two simple nonlinear functions, and then there's an equality constraint. It's not supposed to be completely analogous to a power system problem, but it's close. And the idea is that either variable can be simply held at 0 and be out of the problem. And so if there's two variables, well, you can enumerate the u sub I, and there's no time steps in that example. The ui values can be both 0, can be 1, 0, or 0, 1, or 1, 1. And you can solve the 0, 0 you don't get to equal you don't get the equality constraint. Otherwise, and you can just enumerate the solution. Then you can go and show that you can solve the problem with this Lagrange relaxation method. And that's a good one to go back to and look at it when you get a little confused. But this one says that the important thing is right here. Lambda is fixed in this part of it, and over here, these guys I should put fixed here. I'm going to fix the P and the U, and I'm going to maximize over lambda. So lambda, variable lambda. Here, these are variable, and the lambda is fixed. So here I'm relaxing on this side. I'm saying, okay, now I'm going to say, all right, you got me a P and a U value for every generator at every time step. Now, keeping those, I want you to maximize this function over lambda. This is where we adjust lambda. All right, so let's go back and start looking at this then. And this is the essence of the Lagrange relaxation method. Let's see, I think or are we not? Yes. So, our old Lagrangian method. Now, here's the nasty part. Once again, is that there's a summation over T. There's a summation over all the units. Now remember that this could be like 1 week every hour, so 168, and I could have let's say a small number, 50 generator units. What would that be? That's 8,400. Okay, that's a lot of combinations. 8,004. You can't sit down and enumerate them. A computer could, but you don't really want to do it that way. You don't want to do it that way. So, once again, this is Fi of Pi plus startup Ui of T. Okay, there's my cost part of it, plus sum T equals 1 to T lambda of T times, and for every hour we have a loading constraint, T minus I equals 1 to N PIT Ui of T. Now, I'm going to do something. I'm going to rewrite this, and I'm just going to take this second term apart here. So L equals these two sums, Fi of PIT plus startup Ui of T plus, okay, I'm going to take this part out and say that's equal to T equals 1 to T lambda T P load T. Now, if I am optimizing and I'm relaxing lambda, I'm holding the value of lambda constant, well then this is a constant. So I can sort of ignore this one in the first part. So we'll put a big X across there. We're not going to look at that, and then we're going to say minus T equals 1 to T, I equals 1 to N, and that's lambda of T, Pi of T, Ui of T. Okay. Now, notice now that I now have a sum over T and over N, and I have a sum over, let's put it in here, T I equals 1 to N. So I have the same sum. So let's rewrite it, and I'm gonna change where the position of the summation. It just, that doesn't change anything. And now I'm going to put a great big bracket, and down here I'm going to say t equals 1 to t fi pi plus startup ui of t minus lambda of t pi of t ui of t. Now what I want you to notice, is that what I'm doing here is for each, this summation in here is for each generator, and it's across all of that generators, all the time periods, just that generator. So this applies to generator I. It applies to generator I, and the idea is that I've separated. And then I just do it for every generator. I sum it over all the generators. But when I'm looking at this thing, this is our Lagrangian. I only look at generator I. I don't have to know anything about what's happening with with the next generator. And what we've done is we've separated. We've done a separated over the generators. Okay, and so let me say the following. We can solve. Remember, we end up wanting to minimize this, so we want to minimize t equals 1 to t fi of p plus startup ui of t minus lambda of t pi of t ui of t. Minimize this for each gen and each gen I, and you do it one at a time. That's the part that's so useful here. You just do it. You do it for each generator one at a time. Now remember also that this guy is fixed. At this point, we haven't adjusted it. And in the examples that I give in the book, we start out with all the lambdas equal to 0. So, it turns out that this is the heart and soul of this technique, is that we now have a problem like this. And notice what we have. We have a one generator schedule. A one generator schedule. One generator. Remember when I had 2 generators or 4 or something? I had all the states listed. So let's do, and I'm going to solve this with dynamic programming. So here's my states, and my states are u equals 1 or u equals 0. And so here's t equals 1, t equals 2, t equals 3. And you remember I had these. This is the way I did this before. I had these states, and I just put dots. Well, rather than having 4 states for 2 units, or 8 states for 3 units, or 16 states, etc., 2 to the n states, n is 1, so I only have 2 states. Oh, that's so it says, and I'm going to start out here. So it says the only paths that I need to worry about are the path that goes up here or the path that goes this way. Now, if it goes up, there could be a startup cost. I'll put S here. From here, it could go and stay on, it could come off. This one could start or stay like this. So from then on, it's always got this this pattern of at each state the generator could go off or it could stay where it is. Well, it turns out that we're trying to minimize this thing. We're trying to minimize it, and this gets to be it is a very simple dynamic program. It's a very simple dynamic program. By the way, we're not going to give you any and I should put come here. I should put. Let me get this back up here. This should have an S. This should have an S. It depends. If it stayed off and then it started. So this goes up. Remember, so this is a startup. So you have to put the S. I'm not going to give you any startup costs in there. It's hard enough to figure out exactly how you do this method without getting all the details at the very beginning. All right, now it turns out then that and we're subject to the we said we're gonna let's draw it again. Min Q lambda over P and U lambda fixed, and that's equal to over each generating unit I equals 1 to n, and then it's minimize the sum t equals 1 to t. Here we go. Fi of p plus startup ui of t minus lambda pu. So this is t and this is I of t and I of t. So if I'm going to minimize this, then I need to go back to my up and down, and of course the pi ui minimum is less than pi is less than pi max ui of t. So it's got to obey the unit up and down constraints. So without looking at the startup cost, I want to minimize this function fi pi minus lambda of t times pi of t. This is when ui of t equals 1. If ui of t equals 0, okay, well the whole thing is 0. Okay, the whole thing is 0. Now, I'm going to take the derivative with respect to p of this thing, f of p minus lambda p, and that's going to give me df bp minus lambda equals 0. And it has a solution simply by making. We say the solution is where, I'm sorry, df dp is equal to lambda at p equals p sum optimum. Now, in the book, there's the equations for 14a, a, b, and c. Either the problem with this is that when you go to solve this, you may have the unit forced to its minimum. If the optimum, and the simplest is to say, well, let's go back to our linear incremental cost function. So here's df dp. Well, if lambda is here, there's the p. Well, what if lambda is here? Well, then p is forced at its min. If lambda is up here, it's forced at its max. So it either ends up at its min or it ends up at the solution where the derivative is equal to lambda, or it's at the maximum. Now, one thing I want you to notice is, come back here again. This thing, if u is equal to 0, it's 0. And we're trying to minimize, and many times this thing will come out to be negative. So we start out with t equals 1. We're going to start out here, and we're going to say, well, either I'm going to go up there or I'm going to go down there. Let's forget the startup cost for now. Here's u equals 0, u equals 1. If it goes up here, then fi of p minus lambda p is negative. And that means that I'm minimizing. That means that I'm adding up something that's negative. I'm reducing the overall function. If it's positive, then it'll stay here. So down here, f of p minus lambda p is positive. Okay, and it'll just stay down there at 0. So you actually now do a one generator dynamic program. It's one of the reasons that you have to teach the dynamic programming, and incidentally, if there were startups, we would have put them in the problem. If there were minimum up, well, once you've turned it on, then you can't, then this path is no longer valid. You can put all of those kind of things, but you'll have to do it for one generator at a time. One generator at a time, and you get a set of solutions. Now we get all done, okay, and we now have min, okay, and it's the min over I equals 1 to n, t equals 1 to t of fi of p plus start ui of t minus lambda t pi of t ui of t. Okay, this set of variables, this thing now has a value that we have minimized, and we've minimized that over pi of t ui of t, lambda fixed. Okay, that's the so-called q not g, q of lambda function. Well, now we're going to come back and we're going to say, okay, now I want to say whatever this came out. Notice that whenever we did have u equal to 1, we get a value up here. In this case, pi of t equals 0. Here we get a pi of t equal to some optimum value between its limits, or else at one of the limits. But we get a number, not a 0. We get a non-zero number, whatever. So I have a p value and a u value for every time step for every generator. And now I'm going to do something with the lambdas. And now I want to maximize q of lambda over lambda. That's my variable with fixed p I t u I t. I'm going to fix the pi and the qi, and I'm going to solve it by adjusting the lambdas. Well, you gotta this thing's the simple. It's a very simple way of doing it. It's a very simple, what we call a gradient method of doing it, or hill climbing. It's the simplest mode. I did not want to get in this textbook into deeper methods of doing this. There are better methods than this, believe me. And so we're going to say for E, we're going to say lambda of t is lambda of t, and you do this for each t plus d lambda of q of lambda times alpha, and alpha will equal 0.01 if dq of lambda d lambda is positive and alpha equals 0.002 if dq d lambda is negative. Okay. And it says that we just take the value, you start out with some value for lambda. Let's say lambda is 0. And you keep creeping up on some number, lambda, and you creep up on it, lambda, for the next iteration. And every time this thing is positive, and so I'm going up, and then all of a sudden it's negative. And now I'm going to start decreasing it, but I'm going to decrease it in smaller steps. So that's what it is. And then if it gets positive again, I'm going to go up in real tiny steps. It's just you step, and then start backing up because you've gone too far. And it works. It works for these examples. That's as far as I need to go here. With this, but let's look at this function again. Q of lambda is, and I'm I'm going to do this for every time step, okay? And so it comes out. It comes out that once I fix PIT, UIT, and lambda's the variable, well, then my whole, remember I had this big double, t equals 1 to t, I equals 1 to n. That whole thing now, the P and the U are known. They're constants. Well, the first thing disappears, and the only thing I've got left is the lambda, and I've got the following. I've got I've got this times the Fi of Pi plus the startup Ui. Well, this I don't need this term anymore because it's a constant, and I've got plus t equals 1 to t, lambda t, p load. Well, the load is a constant. So now I have that part, and then I have plus the sum over t, and, pardon me, this is the I equals 1 to n, and I have lambda pu. And of course, these are fixed numbers, so I just I do have a number in there, but they're fixed quantities. This is a fixed quantity, and so what I end up with by pulling the lambda outside here, and you notice that I have a t. So for each t, t equals 1 to n or to t, pardon me. I have this, and I have a lambda in here, times p load minus the sum I equals 1 to n pi of t ui of t, like this. And now that's q of lambda, and dq d lambda. Well, if I take the dq d lambda, I just get this is equal to p load of t minus the sum pi of t ui of t. So all I have to do is say, is this positive or negative? Well, what that means is that you solved it for pi and u. Does that sum over all of the time steps? This is a t equals 1 to t. Over all the time no. Over all the units. I did it wrong. I pulled the time out. This is the units. Pardon me. This is I equals 1 to n. So I sum over all the units, and for a certain time interval, the ones that are on, does it equal the load? Is it, or better, is it greater than the load or less than the load? That's the indicator of whether I raise or lower lambda. So you can think of the problem as I start out with a bunch of hours, and I start and I have a very simple procedure for adjusting the value of lambda. Start out with the lambda is equal to 0. Now in your text you have this example 4e, and I think, yeah, we go through 5 iterations. I go through 5 iterations, and that gets you fairly close. I wrote a computer code that goes, how many? It goes more, I said that there is never, it never reaches a perfect solution, but what we're going to do, I'll spend a little bit of time on this, looking at the book, the sample, and this is because what I'm going to ask you to do is to solve a similar problem to example 4e. So you need to go through that example and understand it, and then you can just do the homework problem with no difficulty. But you have 3 generators. I'm not going to write it out. This is example 4e. You want to study this. And you have 4 hours. The 4 hours look like this. And so you have a load of 170. Then it goes up to 520. Real systems don't do this. real power systems don't suddenly jump. Well, I shouldn't say. If you were looking at a very large system, it could go up by that quick. And then up to 1100, it doubles again up to 1100 megawatts, and then it drops back to 330. Okay, so that's the schedule of load. The load takes 2 steps up and 1 step down. End of problem. T equals 4. So here's T equals 1, 2, 3, 4. So capital T equals 4. That's the problem, and you're given generators, and you note that all 3 generators have to add up to 170 in hour 1. All 3 have to add up to 520 in hour 2. All 3 to 1100. All 3 to 330 in the last hour. Now, I like to start problems. I don't want to preload the problem in such a way that it gives me a better shot, because then, believe me, folks, that can get you into a lot of trouble. I like to start out, so I say hour, 1, 2, 3, 4. And I say lambda, and I'm going to say at the beginning, everybody is 0. Lambdas are 0. If that's the case, U1, this is the U2 and U3 are all 0. Every hour, every generator is off. It occurs to me you could say that's the absolute 0 start. Everybody, and all the generators, P1, P2, P3, they're also zeros. And you say, well, what good is that? Well, hang in there. Now here we have P load minus the sum Pi of t, Ui of t. Okay? Well, then this is just equal to 170, 520, 1100, 330. Okay? And the generators are all off, so I don't have any generators that on, but later on I'm going to solve a standard economic dispatch, so I call that P1 EDC, P2 EDC, P3 EDC, meaning later on I will have committed some units during each hour, and during those hours when I have enough generation to equal the load, then I'm going to solve an economic dispatch and put the numbers in here. If a unit is is offline, meaning U equals 0, well then it will come up with a 0 for the EDC, but the other two will be in economic dispatch. Well, this is zeros for everybody, so this is the starting point. And one of the things that we did in here is that we add up the FI, I can't write this, the sum of FI of P. Am I doing that right? Yes. And I would sum the economic dispatch solutions costs, and then at the bottom I would sum all of them. So I would sum all of that, and that's the sum over T and the sum I FI of P. This is at the economic dispatch. We called that J star. Okay. And it's easy to figure out what the value of Q and lambda is. It starts out at 0. Now, this is the one place where I had to do something to make the problem work. If there was no feasible way with the units committed to meet the load at all, then I just threw a very large number in there, 10,000. And so at the beginning, this thing will have 10,000 for each generator at the start, okay? And that's why this thing comes up with a value of 40,000. It's because I've added 4 times 10,000. So it's 40,000 at the start. Did I put too many zeros? Yes, no, I'm okay, 40,000. As soon as you get an economic dispatch solution, then that starts to come down. Okay? And what you want is you want the Q of lambda to come over to the J star. And we created this variable called the gap. I should say Bertsikis and his crew. The gap is J star minus Q star over Q star. And it's not defined when Q is 0, obviously. Well, now, so if this is the case, remember that our P load minus the sum P times U in there, you end up with, let me get it right here, that our table had, here's T equals 1, 2, 3, 4. And we had 175, 20, 1100, 330. Okay. Let's look at, and in the book we took the example for unit 3, and that's the one that's got this 1100 megawatts. And here it is. And it turns out that its solution ends up like this, and then it turns it on during hour 3, and then it turns it back off. That's the solution. And so here, P3 equals is P min, P3 min, and here it's also P3 equals P3 min, but here P3 equals P3 max, and here actually here P3 equals 0, P3 equals 0, wait a minute, yep, and P3 equals 0. The min cost, because, and here the overall cost function goes negative, and it's minus 700. And then we come back down here, and so I can by putting this unit on at its max and then coming down here, it's going to force a negative. Okay, now this is for P3, and so when we do the next hour, we've got let's see, T equals 1, 2, 3, 4. Lambda. Now, I didn't show this, but the next, I should have done this first. I need to backtrack here, and I need to solve for lambda for iteration 2. I'm sorry, for iteration 2. Well, the gap, remember, was these values. This is the value: 170, 520, 1100, 330. Those are positive numbers because the P times U is 0. So this is positive. So then I increase lambda, but I multiply it. So my lambda values come out to be 1.7, 5.2, 11.0, and 3.3. So those are the new values. Lambda, 1.7, 5.2, 11, and 3.3. And they were obtained because of the load. There was no generation on. Therefore, the dq dp is positive. And I have that alpha of 0.01, pardon me, 0.01. So now I have some lambdas, and when I did this solution up here, I used lambda equals 1.7, lambda equals 5.2, lambda equals 11, lambda equals 3.3. Okay, that's how I got that next set of solutions. Well, it turned out after the first iteration that U1, U2, U3, I still didn't commit anything the first hour or the second, is that right? Or the second hour. But the third generator got committed. Pardon me, in the third hour, the second and third generators got committed, and nothing happened here. And so then I solved for P1, P2, P3, and it's 0, 0, 0 because the units are off. Same thing for this hour. And then this thing should be 0, 400, and 200, 0, 0, 0. So now I've turned generators 2 and 3 on during the third hour. And now when I do this P load minus the sum P times U, this stays at 170, this becomes 520. Now this goes down to 500. That gap starts to get closed, 330. So this number has changed. I still can't do an economic dispatch because I don't have enough generation on to meet the 1100 megawatt load. So I'm still at 4,000, etc. And yet the Q variable starts to change. So it shows you each iteration in the textbook. Each iteration in the textbook. And remember that over here I have P1, P2, P3 for economic dispatch, EDC. That one is, if there's enough generation to meet the load, then I can do an economic dispatch. Else I just shove this 10,000 in there. And so this is economic. This is the solution of this single dynamic program run for the generator, for each generator individually. And I will show you a graph, if I can here. Let's see. Yeah. I don't know. This is a different printout. I'm not going to put this in the notes because I'm not sure that it corresponds exactly to the example in the book. Here is this function, and the one function is continuing to drop. So this is J star. Here is Q of lambda with a star. And you notice that they do come together. They do come together. It plots that as it iterates. I'll try to, if I can find it. There is a computer solution output of the example in the book that might help you as well. The homework problem, as I say, you will be doing a homework problem that's not the same identical, but it's very close to this example in the book, and you need to work that through. And when you get done with that, that'll get you pretty far into understanding the Lagrange relaxation method. If in the future you ever have to do a 1-0 programming problem and you don't have a code for it, then you need then you can use Lagrange relaxation like we've shown here. Okay, so that being the time limit from 5:15, pardon me, we are done for another lecture, for another week. My intention is to let me put this at the very end, just as a note to everybody. Homework is graded by Friday, on starting Friday. Hunjin gives me the solution, or give the grading over the end of the week. So I pass him a solution on Friday, and he can do the grading starting Friday or Saturday, whatever he does. So this week I will also put homework's solutions into the Google Drive on Friday. Okay? You've been given strict times to turn the homework in by Friday. If you don't get them in by Friday, we're not going to, unless you're sick or something. We had one student who started late. I gave him 1 week. That student gets an extra week to do the work because he started late. And but the second homework problem, no. I'm going to communicate with him. But for others, if you did not get it in on Friday, that's it. You can turn it in and we'll look at it, but it's not going to be given the points. And we will see you all next Tuesday when we start another topic, fuel scheduling and so forth. Okay? Bye-bye.